This video lecture is meant to cover the information from Unit 13 on gas laws, objectives numbers 1 and 2, which say that you can define pressure, temperature, and volume, and convert air pressure units, temperature units, and volume units, and to define the relationship between Kelvin temperature and the average kinetic energy. Both of these objectives come from Chapter 13, Section 1. We're going to start out with a little video clip to help you visualize the difference between solids, liquids, and gases.
The states of matter are gas, liquid, and solid. Gases assume the shape and volume of their container. Particles of a gas are separated from each other, move in straight lines, and in a completely random manner. They change direction only when they collide with each other or the container. Liquids have a definite volume and assume the shape of their containers. The particles of a liquid are closely spaced, and so their motion is still random but much more limited. The particles slip past and collide with near neighbors. Solids have a definite shape and volume. Particles of solids are in fixed positions and collide only with near neighbors.
Alright, so even though that video showed you the difference between solids, liquids, and gases, we are just studying gases in this unit. So if we were to further clarify what the properties of gases are, they do behave as a fluid. Gases can flow. They have a low density because the particles are so very far apart from one another. They are highly compressible, which means that they can be forced under high pressure for the particles to become pushed together and to take a gas that looks like this. If you put it under high pressure, those particles can be pushed together and actually can be turned into a liquid that looks like this down here. Gases are greatly affected by changes in pressure, temperature, and volume, and so that's going to be the focus of our first lecture today: pressure, temperature, and volume. Turns out solids and liquids are not affected nearly as much by changes in pressure, temperature, and volume, and the question that I'm posing to you is why? Well, if you look at these molecular representations of solid, liquid, and gas, you can see that the solid and liquid they're already pushed together pretty closely. They're already packed pretty tightly compared to a gas. And so because gas particles are so very spread apart, that they are easily affected by pressure, temperature, and volume. We're going to be, the focus of this chapter is going to be talking about some gas laws, which are basically a couple of mathematical equations that we'll be using. But before we can begin to study the mathematics of gas behavior, we have to first understand what these three properties are: pressure, temperature, and volume, and how they affect one another. Pressure. Defining pressure. It is the force exerted by a gas on a given surface area. It is the result of simultaneous collisions of billions of rapidly moving particles of a gas with the walls of the container. There are several different pressure units that we could use, and you will see these from time to time. The unit that we will primarily be using is something called an atmosphere, abbreviated as ATM. But the official worldwide unit of pressure is the kilopascal, which is abbreviated kPa. Millimeters of mercury is a unit that has been used and is still used by weathermen today. When you look at the air pressure, they'll refer to it as millibars, which is the same thing as millimeters of mercury. And then there's pounds per square inch, and you're probably familiar with this pressure unit if you've ever had to inflate a tire, either on your car or on a bicycle. There's a number that you have to inflate your tire to, and that unit is pounds per square inch. So there's lots of different pressure units. The ones that we'll be seeing most of the time in this class are atmospheres and kilopascals, sometimes millimeters, and very rarely pounds per square inch. But that's the one you're maybe most familiar with on your day-to-day activities. Converting the units. Since there are 4 different units for gas pressure, we need to know their equivalences. so that we can easily convert back and forth between these units. So we know that 1.000 atmospheres is, first of all, that's the amount of pressure if you were standing at sea level. So you're at the ocean, you're standing at sea level. The weight of 1 atmosphere is on you at sea level, and we call that pressure 1 atmosphere. So that's where that unit comes from. That is equivalent to 101.3 kilopascals, which is equivalent to 760.0 millimeters of mercury, which is equivalent to 14.69 pounds per square inch, psi. So here's an example. A gas exerts a pressure of 151.4 kPa. What is the pressure in millimeters of mercury? Well, with any conversion problem, the way to start this is to start with the number you are given. The measurement you have is 151.4 kPa. And from there, you will set up a conversion fraction bar. So that means you set up a multiplication symbol, a conversion fraction bar, and then we set up our units. Now notice that kPa has to go on the bottom because that's what we're trying to cancel, and millimeters of mercury has to go on the top because that's what we're trying to convert to. And then the numbers that go in here are the equivalences. So how many kPas are equal to how many millimeters of mercury? Well, 101.3 kPas is equal to 760 millimeters of mercury. Right. What you will do is, of course, notice that kPas will cancel, and then it's just a matter of calculator work to determine that your answer is equal to this answer that your calculator gives you, 1,135.87364 millimeters of mercury. Clearly, this number needs to be rounded. And so on these conversion fractions, go back to your original measurement, in this case 151.4, and we notice this has 4 significant figures. So that's how far we're going to round this final answer right here to 4 significant figures. So that would be 1136 millimeters of mercury. Now, talking about this millimeters of mercury, this is an old style mercury barometer. You can see here this diagram. This is a tube with liquid mercury in it. It is about 1 meter long. And what you can't see down here is this tube is essentially an open straw, an open tube, and it's sitting in a container of mercury. Well, the pressure from the outside world is pushing on this tube all around, but since this is an open beaker of mercury in here, the air pressure pushing down is forcing the mercury to go up this tube, and however high the air pressure is pushing the mercury up into this tube, we can then see, we can measure the distance from where the mercury travels down here in the beaker all the way up to the top of the tube, and 1 atmosphere gives you about 760 millimeters. So that's about 3/4 of a meter, which is why you can see the meter stick here is there for reference. This particular barometer has inches, and I believe it's somewhere in the neighborhood of 29 or 30 inches is standard temperature or standard pressure. So you can see right here, if you look really closely, you can see that's where the mercury comes to. So it's the distance, the air pressure is so strong it can push the liquid mercury a certain distance up inside this tube, and so that's how we measure mercury in terms of length. That's how we measure, that's how we measure pressure in terms of length, the length of the mercury inside this tube. All right, moving on to talking about temperature. Temperature technically is not really a measure of heat. A better definition, it is the measure of the average kinetic energy of molecules. We're going to abbreviate kinetic energy as KE since it's a little simpler. But it's a measure of, temperature is a measure of the average kinetic energy when you are using the Kelvin scale. All right, and we'll talk about that in a moment. Another way of saying this is that it's a measure of the motion of the molecules in a substance. Now here's how you can kind of think about it. If you have a temperature of 0 Kelvin, then that's 0 movement of molecules, and we would call that temperature. That's called absolute zero. Right? Now, because 0 Kelvin is 0 kinetic energy, it then stands to reason that 100 Kelvin is twice the kinetic energy of 50 Kelvin. So when you double the Kelvin temperature, you have doubled the kinetic energy. This is not true for Celsius or Fahrenheit because 0 Celsius and 0 Fahrenheit do not translate to 0 kinetic energy. So we will be using Kelvin temperatures for everything we do in this unit. Okay, but the problem is we typically measure everything with the thermometers we have are all in Celsius. Right, so we're going to have to know how to convert back and forth between the units of degrees Celsius and degrees Kelvin. Now notice a minor point here. Degrees Celsius is always abbreviated with a degree symbol, but degrees Kelvin is not. And this is just a convention that seems to be employed universally. Okay. Converting the units is not necessarily the same way we convert pressure or volume. We have this handy equation because Kelvin is the Celsius temperature plus 273. So let's try an example. Liquid nitrogen boils at negative 196 degrees Celsius. What is this temperature in Kelvin? Right. Well, we start with the Kelvin equals C plus 273, and we know our Celsius temperature is negative 196. So we're going to substitute negative 196 in for the C of this equation. So this will look like this. Kelvin is negative 196 plus 273. And you just do that calculation in your calculator and you discover that Kelvin is then equal, the Kelvin temperature is then 77 K. Right, so that's how you convert temperatures between Kelvin and Celsius. This video is going, well, I'll let it speak for itself.
Are you ready? You wanted them, now you've got them. It's atomic energy with molecules in motion.
Molecules are atoms that are bonded together. They're hard to see and they're difficult to measure. But if we look real close, we can see them moving. They vibrate, they rotate. It's like they're proving that nothing's at rest, that everything swirls like an ocean. It's kinetic energy, molecules in motion. Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
If molecules absorb energy from their surroundings, they move faster and faster. That's quite astounding. Just like the kinetic energy rises with molecular motion, the temperature also increases with all this commotion. Kelvin is a unit of temperature, like Celsius and Fahrenheit. And temperature is a measure, and be sure to get this right. It's a measure of molecular movement. So let's review and delve in. Energy rises with molecular movement, as does the Kelvin. Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
In liquids and gases, molecules can also move around from region to region like a river or a cloud. The movement of objects is quite a cool notion. It's kinetic energy. Come on! Molecules in motion.
Molecules are moving all the time.
Molecules in motion.
Molecules, they keep us energized.
The concept that we're going to study is volume of gases, and so we need to define it. Volume is a measure of space occupied by a sample of matter. The units that we're going to see in this class are going to be milliliters and or liters. And so just converting the units, should be most definitely a review that 1 liter is equal to 1,000 milliliters, and you'll need to be able to comfortably go back and forth between those two units. So here's an example. A liquid has a volume of 48 milliliters. How much is this in liters? And if you get stuck on whether or not you're dividing by 1,000 or multiplying 1,000, this is why conversion fractions take out the guesswork, right? So if you follow the pattern of what we do for conversion fractions, you start with the number you're given and you set up a conversion fraction, right? So just like that. You know you have to put milliliters in the denominator because you want those to cancel. Liters, therefore, has to go on the top. And now all you need to remember is that 1 liter is equal to 1,000 milliliters. And now you know that you are dividing by 1,000. So take out the guesswork if you don't really have that intuitive sense. And so now it just becomes calculator work. 48 divided by 1,000, which means you're moving the decimal point to the left 3 places. So this becomes 0.048 milliliters. And in this number, we have maintained the 2 significant figures in the original measurement. So that's how we convert volume. To finish up our discussion here today, you're going to see an abbreviation STP, which stands for standard temperature and pressure. And so gases all need to be, when we talk about the volume of a gas, sometimes there are standard conditions that we report the volume to be measured at, because if you change the temperature of the gas or you change the pressure of the gas, you will also be changing the volume. So in order for volumes to be kept consistent, many times they're measured at standard temperature and pressure. And so this is something you will need to know, that standard temperature is 0 degrees Celsius, which of course is 273 Kelvin, and standard pressure is 1 atmosphere, which of course is the same thing as 760 millimeters of mercury, which is the same thing as 101.3 kilopascals, which is the same thing as 14.69 psi. All right, so this is where we're going to end our video lecture today. We'll see you in the classroom for some unit conversion practice.